Okay, in this video I'd like to revisit what it means to be a linear transformation. Previously we've mainly been looking at linear transformations that went from a vector space Rn into Rm, but we can also talk about a function or transformation from any vector space to any other vector space. And it's the same two axioms we've seen before. Basically, T just has to behave nicely with respect to sums and constant multiples. And I'll come back to this in a second. But it turns out we've already seen lots of functions that do this that aren't just functions from vector space to vector space. So for instance, our differentiation function, the act of taking a derivative, turns one polynomial into another polynomial. And things that we know about the derivative, we know we have a sum rule. The derivative of a sum is the same as the derivative of the individual parts. Or in other words, d of f plus g, derivative of f plus g should be the same as the derivative of f plus the derivative of g. And same thing for constants. Derivative of a constant times a function should be the same as a constant times the derivative of the function. Same thing is also true for integrals, but at least this example is written is for sure going to be a linear transformation. But let's get to something new, something we haven't seen before. I'm going to define a new transformation that goes from a set of polynomials or a vector space of polynomials into a vector space of matrices. So T of ax plus b, which is a polynomial in P1, the polynomials of degree 1 or less, is getting mapped into a set of 2 by 2 matrices. So T of ax plus b is ab 0 minus a, and I want to try and show that that function t is a linear transformation. So first I need to take t of u plus v and t of u plus t of v. Okay, so I need to start off with what exactly do I mean by u and v. One of them is going to be ax plus b, and the other one, I guess I'll use cx plus d. And so I just copy the same thing. Okay, so on the top we're supposed to add two polynomials. Ax plus b plus cx plus d would be a plus cx plus b plus d, combining like terms. And then t of something, let's see, the coefficient on x goes in the top left corner and with a minus sign in the bottom right corner. So a plus c in the top left minus a plus c in the bottom right. We get a 0 in the bottom left, and we get the constant coefficient in the top right. Okay, let's work downward so we have a little bit more room. Over here, if we take t of ax plus b, that's exactly this matrix, ab 0 minus a. T of cx plus d, c is playing the role that a was previously holding, so t of coefficient of x would go in the top left and negative in the bottom right. The constant d would end up being in the top right corner, and then a 0 in the bottom left. And then matrix plus matrix, we add corresponding entries, so that would be a plus c, b plus d, 0 plus 0, and negative a plus negative c. And you'll notice these two are equal. We would also have to show t of ku and t of u multiplied by k are going to give you the same thing. I'm going to skip that for now. What I wanted to talk about is where exactly these additions are happening. When we're taking this sum right here, t of u plus v, u and v were polynomials. They were in P1, and so this addition is how would you add two polynomials. Over here though, t of u plus t of v, t of u spits out a matrix, t of v spits out a matrix. So this plus right here is actually talking about sum of matrices, because that's how we actually did that plus. So this is the sum in the set P1, whatever it means to add things in P1. So we add polynomials differently than we add matrices. Matrices, we add corresponding components. Polynomials, we have to combine like terms. They're similar, but they're not exactly the same. So that's essentially what we mean when we say that the transformation acts nicely with sums. The sum in vector space V is compatible with the sum in vector space W after you take this transformation.